MS Ramaya University of Applied Sciences.
Hello students, in this session of Control System Lab videos, we will see how to plot a root locus in MATLAB and find the stability of the system. First open MATLAB and in MATLAB select New Script. So here we'll type the program. So we're going to type a program on how to plot the root locus. First, let me define the variable s. I will define it as syms of s. So that is the variable that I am going to use to write my transfer function. My numerator num is equal to 1. And I will define the denominator den is equal to sym to poly, that means system to polynomial. So my denominator is s into s plus 1 into s plus 2. This method of entering the denominator is used when we know the location of the poles but we don't know the denominator polynomial. Okay, let me define the transfer function. G is equal to transfer function of numerator comma denominator. So this is the transfer function. Let me save the program first. I will save it as rlocus. Yes. So as you can see here, this is the transfer function, 1 by s cube plus 3s square plus 2s. Now, so this is the transfer function. Let me plot the root locus for this transfer function. I will type figure so that I get a new window. The command to plot root locus is given by rlocus, and inside the parenthesis you write g. Let me run. So this is the root locus plot for the given transfer function. So as you can see, there is a pole at s is equal to 0, there is a pole at s is equal to -1, and also there is a pole at s is equal to -2. So if you click anywhere on the root locus, you can see the various parameters like gain, the position of the pole, etc. Let me close this window. Now this is the transfer function for open loop. Let me write a closed loop transfer function. So to do that, let me include a gain factor called k. So I'll take the gain factor as 1 initially, and also a feedback factor h, which is also 1. The gain factor and the feedback factor. Let me write the transfer function for a closed loop. M is equal to feedback of, in the forward path we have two elements, which is the gain and the forward path transfer function, which is g, and h, which is the feedback transfer function. So M is the closed loop transfer function. So let me plot the step response of the closed loop transfer function. So I'll type figure to open a new window, and then step of m, which gives me the step response of the closed loop transfer function. So this is the root locus for the open loop transfer function and the step response for the closed loop transfer function. So if I click on the pole, the gain will always be 0 because the root locus is nothing but the path taken by the pole. So the intersection of the imaginary axis and the root locus determines the critical point or the point beyond which the system becomes unstable. In this case, as you can see, it is 6. So let me enter 6.61, and you see that the step response, the amplitude goes on increasing Therefore, the system is unstable when I increase the gain beyond 6.28. Now the gain is 6.61. So it goes on increasing. So let me find out the exact point at which the imaginary axis intersects the root locus. I'll enter the value of k as 6, and when I run, you see that I get sustained oscillation, which means that the system is critically stable. Now I'll make k as 1, and let us find out the root locus for the closed loop transfer function, R locus of M, which is the closed loop transfer function. Now when I run, we get three plots. One is the transfer function, the root locus for the open loop transfer function, step response for closed loop transfer function, and also the root locus for the closed loop transfer function. So we get three plots here. So as you can see, the poles for a gain of 1 in the open loop transfer function gives you poles in these 2 points. So when the gain is 6.09, the poles in the closed loop transfer function shift exactly on the imaginary axis. Let us see what happens when k is equal to 6. So k is equal to 6. And when I run, you will see the closed loop transfer function, the root locus, the poles will be exactly on the imaginary axis. So as you can see, when the gain is 6, the poles are exactly on the imaginary axis. When the gain is 0.385, which is a point on the real axis, you will find that for the closed loop transfer function, the root locus will have the poles placed on the real axis. And you see, for 0.38 approximately, you get the poles exactly at that point. Let me click on some other point, say 0.189. Let me change the value of k as 0.189. You will see that the poles are also shifted to that point. See, the poles have shifted to 0.189. So that is all about root locus, which is nothing but the path traversed by a pole as we increase the gain of a system. As the gain increases and the pole shifts beyond the imaginary axis, that is toward the right hand side of the pole 0 plot, then the system becomes unstable. Thank you.
At MSR UAS, we spark your imagination unlike any other.